So hello friends, welcome you all on this YouTube channel. So in the last video I have discussed the problem of the unequal saturation level of the two cities with respect to the differential protection scheme, right? So in the last video I have discussed the concept of the differential protection, and I have also discussed the practical problem that we encounter in case of differential protection. And the problem is that the two cities, even if they have same CT ratio, thus their saturation level will not be the same practically, right? So due to unequal saturation level, the differential relay may maloperate, right? And that will lead to the error, right? Relay should not maloperate. And I told you the reason of unequal saturation level. What is the reason of unequal saturation level? The reason is that the CTs will face the different temperature at different point of the transmission line, so their saturation level will be different even if their CT ratios are the same, right? So this practical problem that we encounter, that is the unequal saturation level, this practical problem can be sorted out using the percentile differential relay, right? Percentage differential relay, that is also known as merge price protection scheme, right? Percentage differential relay is also called merge price protection scheme, right? So the logic is that, see here, it's a very simple logic. Just understand this and you will get the whole concept of percentage differential relay that we have used to avoid the practical problem of unequal saturation level of the two CTs, right? So the logic of percentage differential protection is that 100, if you see two numbers, suppose one number is 100 and second number is 90. So 100 minus 90 will be 10. So that is a low number, isn't it? So that means difference of two high numbers is low, right? Difference of two high numbers is low. Now let us take 100 minus 10. 100 minus 10, 100 is high number, 10 is low number. So difference of high and low number, that is 100 minus 10 is 90. 90 is high number. So the difference of high and low number is high, right? Now let us take 100 plus 90 by 2. Take average of two high number. 100 plus 90 by 2, that is 95, that is high, right? So average of two high numbers is high, isn't it? Average of two high numbers is high. So now let us take average of high number and low number. So 100 plus 10, 100 is high number, 10 is low number. So 100 plus 10 by 2, that is 55. 55 is a low number, isn't it? 55 is a low number. So average of high and low number is low. Average of high and low number is low. So that is the logic of percentage differential protection that we are going to use in percentage differential relay or merge price protection scheme, isn't it? If you have understood this simple logic, then you will also understand this percentage differential relay, right? Logic is very simple. Everybody will understand this, right? So I'm going to use the same logic. Just have a look at it. So let us see how this logic is used to provide this percentage differential protection, right? So just have a look at it. So here, this is the lengthy transmission line, right? this is the lengthy transmission line that we have to protect using the differential, that is percentage differential protection scheme, right? Why we are using percentage differential protection scheme? Because of practical problem of the two CTs. Practical problem is unequal saturation level, right? Why unequal saturation level? Because the two CTs will face the different temperature as different point on the transmission line, so their saturation level will not be the same. Even if their CT ratios are the same, their saturation level of the two CTs will not be the same. So that leads to the problem, right? While providing the differential protection, that's why we have used the percentage differential delay. I told you earlier, right? So here let us see this diagram, the simple diagram. So here you see this, a lengthy transmission line I have to protect using the differential protection scheme, right? Right, this is the lengthy transmission line that I have to protect using the differential protection scheme, percentage differential protection scheme I am using, right? So this is point A and this is point B. So inside this protected zone, if any fault occurs, then the relay must operate, right? And relay should not operate for any fault which is outside this zone. Let us see now. So for percentage differential protection scheme, what we have done, we have slightly modified this circuit. See here, we have connected a restraining coil, right? I am introducing a term which is called restraining coil. So operating coil is the same as earlier, but here what I did, I have introduced a restraining coil in this circuit. One restraining coil is this, another restraining coil is this, isn't it? And this vertical that you are seeing, this is the operating coil, right? Now this is the CT1 and this is the CT2. As before, CT ratio of both the CTs is 100 by 5 and 100 by 5. CT ratio of both the CTs is the same, right? CT ratio of both the CTs is same. CT ratio of both the CTs are same, right? So here also 100 by 5, here also 100 by 5, isn't it? Now let us suppose saturation level of CT1 is 1000 ampere and saturation level of CT2 is 900 ampere, isn't it? Saturation level of CT1 is 1000 ampere and saturation level of CT2 is 900 ampere, isn't it? So we have assumed, right? My aim is to discuss the practical problem of the two CTs, that is unequal saturation level. If their saturation level are unequal, in that case how to provide differential protection, right? So that I have to discuss, right? Now see here, both operating coil and restraining coil have the same number of turns, right? That we have designed like that. So here let us see, this is the practical illustration. See here, in operating coil I told you the difference of current flow will flow I1 minus I2, right? So operating coil current is I1 minus I2. And in restraining coil, see here, restraining coil number of turns n by 2 and n by 2. So and half of this restraining coil having n by 2 number of turns and half of this restraining coil will have n by 2 number of turns, right? Okay, so the operating coil current is I1 minus I2. And what is the restraining coil current? The restraining coil current is I1 plus I2 by 2, that is basically the average. right? Okay, and the staying coil current is I1 plus I2 by 2. That is basically average of current, right? So here operating force is proportional to mmf of the operating coil current, right? Operating force is proportional to mmf of operating coil. Operating force is proportional to current into number of turns in the operating coil, that is I1 minus I2 into N. So operating force is proportional to difference of current. Operating force is proportional to difference of current, that is I1 minus I2. So operating force is basically proportional to difference of current, that is I1 minus I2. So restraining force, now what is the restraining force? Restraining force is basically proportional to mmf of restraining coil. Just like the way we said operating force is proportional to mmf of operating coil, in the same way I will say restraining force is proportional to mmf, magnetic motive force, of restraining coil. So restraining force is proportional to I1 into N by 2 plus I2 into N by 2, right? You know that restraining coil, the restraining coil, in the restraining coil, in half of the portion current I1 is going, and in half of the portion current I2 is going, but the number of turns in both half is same, N by 2 and N by 2, right? So mmf will be, mmf of restraining coil will be I1 into N by 2 plus I2 into N by 2. So that means I1 plus I2 by 2 into N. That means restraining force is proportional to average of currents, number of turns N is fixed. So restraining force is proportional to average of currents. 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 Mind it very clear, right? But the operating force is proportional to difference of currents. Operating force is proportional to difference of current I1 minus I2. Have you understood? Right? That is clear. All right. Now let us go forward. So now let us take case number 1. Let us see. So let an external fault of 1100 ampere. Let us see that whether this logic is working or not, right? Let us see now. So here let an external fault of 1100 ampere occurs at point P1. So then this let an external fault of 1100 ampere occurs at point P1. External fault is called as through fault technically, right? So let an external fault of 1100 ampere occurs at point P1. P1 is a point which is external to the protected zone AB. Then this fault current of 1100 ampere will be seen by both the CTs, right? So CT1 secondary current will be 50 ampere and CT2 secondary current will be 45 ampere. So current in operating coil will be 50 minus 45 will be 5 ampere. CT1 secondary current is 50 ampere. CT2 secondary current is 45 ampere, right? Remember, CT1 saturation level we have assumed 1000 ampere and CT2 secondary level is 900 ampere. What is the meaning? Meaning is that the CT1, the maximum value of current that is seen by the CT1 primary will be 1000 ampere. Even if the current appears more than 1000 ampere, CT1 primary current will see only 1000 ampere because we have assumed that the CT1 saturation level is 1000 ampere. So the maximum current that will be seen by the CT1 primary will be 1000 ampere. So for 100 by 5 CT ratio, CT1 secondary current will be 50 ampere. So even if the current which is more than the 1000 ampere appear in the CT1 primary. The CT1 primary will see only 1000 ampere current because the saturation level of CT1 is 1000 ampere. So 1100 ampere, for 1100 ampere fault current, the CT1 primary current, CT1 primary will see only 1000 ampere because CT1 will saturate at 1000 ampere current. So any current which is more than 1000 ampere, it will see only 1000 ampere current. So corresponding to 1000 ampere CT1 primary, the CT1 secondary current will be 50 ampere for the 100/5 CT ratio, right? Now CT2 saturation level, I told you that we have assumed CT2 saturation level is 900 ampere. So any current which is more than 900 ampere, if it appears in the CT2 primary will see only 900 ampere current. Maximum 900 ampere current will be seen by the CT2 primary because CT2 saturation level is 900 ampere. So CT2 secondary current will be 45 ampere for 100/5 CT ratio. So that's why current in operating coil 50 minus 45 is 5 ampere, right? So operating force is proportional to 5 ampere. So current in retaining coil will be, I told you that it is the average. That means 50 plus 45 by 2, that is 47.5 ampere. That means retaining force is proportional to 47.5 ampere. So retaining force, you see here, retaining force is proportional to 47.5 ampere current, but operating force is proportional to 5 ampere, only 5 ampere, right? So retaining force is definitely more than operating force. So that means relay will not operate even if both the CTs have different saturation level, right? And that's what we desire, that the relay should not operate for any fault which is external to the protected zone AB. Are you getting my point? Right? That's as simple as that, right? That's very simple, isn't it? अगर हम रेस्टेनिंग कॉइल नहीं लगाते तो क्या होता? रिले एक्सटर्नल फॉल्ट के लिए भी ऑपरेट कर जाती कि नहीं, बोलो, और माल ऑपरेट हो जाती. बट ड्यू टू रेस्टेनिंग कॉइल रिले इज नॉट ऑपरेटिंग even for the relay is not operating for external fault, and that's what we desire. We desire that relay should not operate for any fault which is external to the protected zone AB, and the relay should only operate for the fault which is inside the protected zone AB, right? Are you getting my point? See here once again what I told you. I repeat once again what I told you, right? I repeat once again. Listen once again. See here I told you that fault is occurring at a point which is external to this protected zone AB, right? So here this is the fault current, that is 1100 ampere, let us suppose. So both the CTs will see the same fault current, 1100 ampere, right? But maximum fault current which is seen by the CT1 primary is 1000 ampere, because CT1 saturation level we have assumed 1000 ampere, and the maximum fault current which is seen by the CT2 primary current, maximum fault current which is seen by the CT2 primary current is 900 ampere, because CT2 saturation level is 900 ampere. So CT1 secondary current is 50 ampere, right? And CT2 secondary current is 45 ampere by the CT ratio of 100/5. CT ratio, both the CTs are same, only saturation levels are different, right? That is a practical problem of the two CTs. I have explained earlier also, right? So here CT1 primary current is 50 ampere, 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 CT1 current is CT1 primary current is 50 ampere, and CT2 secondary current, CT1 secondary current is 50 ampere, CT1 secondary current is 50 ampere, and CT2 secondary current is 45 ampere. CT2 secondary current is 45 ampere. That means difference of current in the relay operating coil will be 50 minus 45, 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 that is 5 ampere. So operating force is proportional to 5 ampere, but the restraining force is proportional to average of the two current, that means 50 plus 45 by 2, that is 47.5 ampere. So the restraining force is proportional to 27.5 ampere. So definitely in this case restraining force is more than operating force. The relay will not operate. Relay will not operate for this external fault which is external to this protected zone. That's what we desired. The relay should not operate for any fault which is external to this zone, isn't it? Right? Isn't it? Is that clear? Right? So for any external fault or through fault external to the protected zone, the relay will definitely not operate, because we have used a percentage differential protection scheme. Percentage differential protection scheme. Percentage differential protection scheme. Right? That is basically eliminating the problem of unequal saturation level. Right? Now let us suppose if any internal fault occurs at point P2 which is inside the protected zone AB. Let us take another case. Let an internal fault of 1100 ampere occurs at point P2. P2 is a point which is external to the protected zone AB, right? So out of 1100 ampere, 1000, let us suppose 1000 ampere goes to the ground, to the fault point, and 100 ampere goes to the load, right? So now both the CTs will not see the same fault current. Both the CTs will not see the same fault current. And the CT1 primary current, the current seen by the CT1 primary will be 50 ampere, isn't it? Because 1000 ampere goes to the ground to the fault point P2, right? Fault point is P2 which is inside the protected zone AB. So CT1 secondary current is 50 ampere and CT2 secondary current is 5 ampere because only 100 ampere goes to the load, right? Isn't it? So CT1 secondary current is 50 ampere, CT2 secondary current is 5 ampere. So current in operating coil is 50 minus 5, that is 45 ampere, and operating force is proportional to 45 ampere now, isn't it? So current in restraining coil, you know that it is average of the current. So that is 50 plus 5 by 2, that is 27.5. So restraining force is proportional to 27.5 ampere. So operating force is greater than restraining force. Operating force is greater than restraining force. That means relay will definitely operate because operating force is more than the restraining force. So relay will definitely operate for the internal fault. Relay will definitely operate for internal fault even if the saturation level of both CTs are different. Are you getting my point? So the problem of unequal saturation level of CTs can be avoided using percentage differential protection scheme, which is also known as merge price protection scheme, right? Are you getting my point? Yes, that is very easy. If you have not understood, then repeat the video, right? You can again watch the video. That is very simple, right? Logic is very simple. I told you already. In operating coil, the difference of current will flow, and in restraining coil, average of the current will flow, right? So even if the saturation level of the two CTs are different, the relay will not mal-operate, right? And the relay will only operate if the fault occurs inside the protected zone AB, and the relay will not operate for the normal operating condition, and the relay will not operate for the normal operating condition and for any fault which is outside the protected zone AB. That's what we desire. Are you getting my point? Right? Are you getting? Right. So the here so thank you very much. Thanks for watching. Next, the characteristic curve, right, that we will discuss in the next video, right, in the next class. Thank you very much. Thanks for watching.